My name is Jesse Madnick. I'm a postdoc here at the National Center for Theoretical Sciences, based at National Taiwan University. Prior to this, I was a postdoc at McMaster University, and prior to that, I was a graduate student at Stanford. My interests are in calibrated geometry, and in particular the parts of calibrated geometry that pertain to G2 and spin 7 geometry. I'll be reporting on joint work with Darren Cheng and Spiro Karygiannis on a compactness theorem in G2 geometry that is in some sense an analog of a weak form of Gromov's compactness theorem in symplectic geometry. So this talk will be based on an analogy between the even-dimensional world of symplectic geometry on the one hand and the 7-dimensional world of G2 geometry on the other. And in this analogy, the J-holomorphic maps into symplectic manifolds are in some sense analogous with what are called associative Smith maps from 3 manifolds into G2 manifolds, which have dimension 7. So these classes of maps are indeed quite similar. Both classes of maps are, these are conformal maps. They are energy minimizers in their homology class for the p-energy functional. And when these maps are immersions, their images are, in fact, calibrated submanifolds. So the image of a J-holomorphic immersion is a holomorphic curve, and the image of an associative Smith immersion is what's known as an associative threefold, which is a calibrated submanifold, very important in G2 geometry. And so based on this analogy, one hopes that maybe the analytic features of J-holomorphic maps might also be true or hold for the associative Smith maps, and that is indeed what we demonstrate. So we show an epsilon regularity theorem, an energy gap theorem, a removable singularity result, and a compactness mod bubbling theorem. And so taken together, what these demonstrate is that sequences of associative Smith maps with bounded energy have subsequences that converge in a certain sense to a bubble tree of associative Smith maps. And just like in the J-holomorphic map case, we show that these bubble trees have no necks and that no energy is lost in the limit. So this is in some sense about the boundary of the moduli space of such things. So some aspects of the talk are maybe sound a little technical, but as much as possible, I'll be emphasizing these geometric analogies and trying to make the talk as accessible as possible.